Welcome back. In example 3, we've got the integral of e to the square root of x dx. Now in this case, if we try to let u equal the square root of x, which is the inside function, and that oftentimes works for substitution kind of problems, the problem is the derivative doesn't appear with the dx. So we'll have to think about that. If we try to let u equal the whole thing, e to the square root of x, again, the derivative of that is not appearing with the dx. And integration by parts is also problematic because if you either let u equal e to the square root of x or the dv equal e to the square root of x, you get more complicated things going on there. So definitely worth it to explore and try out these different things. But in this case, let's revisit that substitution. Let's try that substitution again. We're going to go back to try and let u equal the square root of x. Something special is going to happen here. If we let u equal the square root of x, the du, the derivative of that, remembering that the square root of x is x to the half power, the du will be 1 over 2 times the square root of x dx. So the reason for that is the 1/2 multiplies in front, and when you subtract 1 from the exponent, you get an x to the negative 1/2, which gives you the 1 over square root of x that we see here in the derivative. Now the thing is, we see that radical x appearing in the derivative again, kind of like in example 2, how we saw the e to the x appear in its derivative. Like when we let u equal e to the x, you see that the derivative is e to the x, so it appears, the function appears in its derivative. So what we could do is think, well, that square root of x can be replaced with a u, and then we can move all the u's over to the left. So we'll actually just start by moving everything over to the left, and note that we can replace the square root of x with a u. So now we've got 2u du equals dx. So what this allows us to do is say, well, we can replace the dx with just something in terms of du. We can entirely replace it in terms of something with respect to u. So let's go ahead and do that. Over here we've got the integral of e to the u, and then the du becomes 2u du. So now the integral is all in terms of u. And this is an integral that you might actually recognize. This is like a u e to the u. This is like a polynomial times an exponential. This one we can use integration by parts on. So we're going to take one more step here to take the 2 out and write it as u e to the u du. And then in the next step, we're going to use the tabular method. Go like this. We're going to use the tabular method, or the streamlined version of integration by parts, to finish this off. So we'll write u in the left column, we'll write e to the u in the right column, take derivatives of u going all the way down to 0. Derivative of u is 1, and then derivative of 1 is 0. And then we can integrate e to the u, which is just going to give you e to the u. Then the uv's that pop out of integration by parts appear in the diagonals. So we end up with 2 and then times u e to the u minus e to the u, and we'll put our plus c at the end there. Now the only last thing to do is go back to x. So we would have, and we'll distribute the 2 as long as we're at it. So we'll have the square root, 2 times the square root of x times e to the square root of x minus, and then distributing that 2, we have 2e to the square root of x plus c. There we go. So not too bad. Turned out that our initial intuition about trying a substitution did end up working out. We just had to do a slightly modified version of a substitution, one where one that can handle the case where the derivative of u doesn't really appear right next to the dx. It's a case where the derivative of u has u inside of it, so we can replace that part with u, and then turn the dx into just a bunch of u's and du's. Okay, so that's one way of doing the substitution. Another way that you might see this is written out, at least, is like this. So this is an alternate way of doing the green part that we did, where we let u equal the square root of x, and then made it all the way down to 2u du equals dx. So all those steps that we took right there, we can do them in a slightly different way. We can start off, again, the same way, so let u equal the square root of x. But then here, we can think about our goal being to isolate x, to figure out how to solve for x, which would mean squaring both sides. And then when we take the derivative of both sides with respect to x, we're going to get or just take the derivative of both sides, you can think, and move the dx over to the right. We're just going to get dx on the right, because the derivative of x is like 1, and then we'll write our dx off to the right. On the left-hand side, we're going to take the derivative of u squared, and so here what we're going to get is 2u du. And we end up at the same place as we did before. We have 2u du equals dx. The nice thing about this way of doing it is that we avoid the derivatives of the square root functions, which can sometimes be a little bit of a headache. So if you immediately solve for x, that gets rid of the square root. And then when you take the derivatives on both sides, you end up with dx solved for in terms of du, or of u and du. And so when you replace the dx out, you don't have to worry about anything being right next to the dx here. You just replace the dx with what it is in terms of u and du, and then make all your other replacements in the integrand. So this is a nice clean way of doing this type of problem, and one that we're going to use going forward. All right. And speaking of going forward, let's head over to example 4, which is the integral of 1 over the square root of the square root of x plus 1. So you have to be a little bit careful here about how far the square root bars go. So inside the bottom square root, on the bottom of the radical, is the square root of x, and then outside that square root is a plus 1. So the radical over the x only extends as far as the x goes. The plus 1 is not inside that inner radical. Okay, so this one looks a little bit complicated. A square root inside of a square root. I mean, geez. But it's not too bad. Let's let u equal that inner part, the inside of this bottom radical. So in other words, the square root of x plus 1. Let's let u equal that. Okay, so if we let u equal the square root of x plus 1, what we can do here is try to solve for x. That's what we talked about in example 3 a moment ago as being a nice technique. If we solve for x, we're going to get u minus 1 equals the square root of x. Square both sides, so we get u minus 1 quantity squared equals x. And now we can differentiate both sides. Now on the left side, the 2 will multiply in front, and you'll subtract 1 from the exponent. Whoops. And then multiply by the inside, which is just 1. So we'll have 2 times the quantity u minus 1 du equals, and on the right side, since we already solved it for x, we get just dx on the right side when we take the derivative. So this is great. Let's take that then and make our replacements. We have 1 over the square root of u times 2 times quantity u minus 1 du. All right. So now what we can do is try to simplify. So we're going to get 2, and then let's see, we'll have 2 and then the integral of u minus 1 over the square root of u du. Now from here, there's a minus on the top of the fraction, so that's great because we can break this into 2 smaller fractions. We'll just have u over the square root of u minus 1 over the square root of u. Fractions can break like that when you have addition or subtraction on the top. Let's do that. And what we'll do is we'll just simplify as long as we're taking this step. So think about how u over the square root of u, what that simplifies to. Let me take a couple of steps on the right side here. U over the square root of u. Well, that's like u over u to the half, which is like u to the 1 over u to the half, which is u to the 1 minus a half, which is u to the half, which is the square root of u. But we're going to use the u to the half version because we're going to be integrating in a moment. So we'll write u to the half. That's what that simplifies to. Then we have minus 1 over the square root of u, which we can write as u to the negative half du. Okay. Put that out of the way. All right, so then we can integrate term by term. And for this first part, remember, we add 1 to the exponent to give you 3/2, and then divide by that to give you 2/3. Then add 1 to negative a half, and you get a half. Divide by a half, which is like multiplying by 2. And then we have our plus c. Now the last step would be to distribute the 2, and then also replace the u's with the square root of x plus 1. So when we distribute the 2 here, we'll have 4/3, and then the square root of x plus 1 to the 3/2. Distribute the 2 to the other 2 to get 4. And then here, usually when we start with radicals, we'll just try to end with radicals if we can. The 3/2 power, a lot of times you just leave that as a 3/2 power, just a stylistic issue, a stylistic kind of convention. But if you do have a half power, then a lot of times you'll see it as a square root. So we're going to write, instead of u to the half, we'll write the square root of u. And remember that u was the square root of x plus 1. It's a giant radical there. Let me make it a little smaller. There. Plus c and box. Okay. So that's example 4. Hopefully you can see how this kind of technique where you let u equal either an exponential or a radical can help out, because when you take derivatives of either of those two, you end up getting a repeat of what you started with. And in the case of the radicals, you can use this new technique that we saw where you solve for x. You can solve for x, and then you take the derivative on both sides. And so you just get dx in terms of u and du. And then everything else, hopefully, if you've done a good choice for u, if you've done a good substitution, everything else in the integrand will also be in terms of u. And hopefully that new integral will be easier to solve. I mean, we did take complexity out of this integral because by letting u equal the square root of x plus 1, all of that stuff inside of the bottom radical just turned into u. And so the integrand just turned into 1 over the square root of u, which made it a lot simpler. So that was a pretty good choice for a substitution. And it worked out that the rest of the problem we were able to finish. But you never know until you try. And so just keep practicing these, and you'll get better and better at them. And pretty soon you're going to love integration, because it's more fun than differentiation, at least in my humble opinion. All right, that's enough for this video. Thanks for watching, and see you next time.